All right. Let's see. So Proposition 12 says it's another construction proof. So the goal is to a given infinite straight line from a given point which is not on that line to draw a perpendicular straight line through that point. So here's my straight line, my infinite straight line, AB, and then my point C that's not on AB. And what I want to do is I want to draw a perpendicular line that passes through C and is perpendicular to AB. Okay, so how do we do that? Well, the first step is this is like a really clever proof, I think. The first step is to choose any point D that is on the opposite side of AB from C. So any point at all. Let's see, am I leaving myself enough room? Yeah, should be fine. So I'll choose this point right here. Um, this is a cool proof because, yeah, you can just choose any old point that you like. You technically, I believe, I'm kind of just saying this off the top of my head, but I think that you can do this proof by choosing a point D on the line. But the reason that it generalizes better to choose a point D off of the line on the other side is because, as you'll see, there is exactly one point that you could choose for D, which is like the point, the intersection point of this perpendicular line. That if you just happened to choose that point D, sort of the whole proof breaks down. If you chose a point D that was on the line that was not that intersection point, then the proof still works. I think I'm just kind of spitballing there. Right. So, anyways, we choose D. Any point D on the other side of AB. And we don't need any justification for doing that. We can just say, yeah, that's possible. I can do that. Okay, step 2. What's next? All right, so next we're going to construct a circle with center C and radius CD. And here's a place where, once again, Euclid sort of makes an assumption that at the time was fine because it's intuitively clear that this is going to happen. But he makes the assumption after making this circle, he makes the assumption that this circle will intersect AB twice in two different places. And again, intuitively, like, yeah, that's pretty clear that that's going to happen. But as far as modern math goes, that's a claim that would probably require some justification. But in any case, here's our circle. So construct the circle C with radius CD. And then I'm going to call these two intersection points, what do I call them? G and E. So G and E are going to be the intersection of AB with this circle. And the only justification that would need to be thrown in there, which is kind of a strange justification, but it's postulate 3. And postulate 3 just says, yeah, you can create a circle. If you have a center and a radius, then you can construct a circle. That's all that postulate 3 says. Very obvious, right? Like, that's the point of the postulates. They should be so obvious that it just doesn't even require any kind of justification. You should hear it and you should just go, yep, no crap. All right. What's next? Right. So next, what Euclid says is he says, all right, we've got this line GE right here. And he says, let's bisect that line. And we were able to bisect that line because that was proposition 10. I-10 that allows us to bisect the line. So I'll say bisect GE. And I'll say at H. So when we bisect it, we'll call that midpoint H. And this is proposition 10 that allows us to do that. And rather than following along with proposition 10 to actually get a decent approximation of this midpoint, I'll kind of use my own little shortcut here. which actually, now that I think about it, I think this is kind of what is done in Proposition 10 anyways, but I'm just going to make two circles. So I guess essentially what I'm going to be doing is I'm going to create an equilateral triangle of side length GE. So I'm making two circles, one with center E and radius GE, the other with center G and radius GE. Then where those two circles intersect is the apex of the equilateral triangle. And this is a claim that I'm just sort of making. It might be obvious to you, and I could prove it, although I don't know that we necessarily have all of the tools from the elements strictly to prove this. But my claim is that this equilateral triangle that we just kind of created, I won't actually make the triangle, but G, E, and then this top piece. If I was to draw a line through this top vertex and through C, it's going to pass exactly through the midpoint of the base, GE. So that's what I'll do. Well, I won't draw the line, not yet at least, because all that we've done, I'm just trying to follow along with the actual proof, all that we actually did was bisected this. But I put in my little circles in there so it's clear how I how I bisected it. Okay, so yep. Next, part 4, and this is really just setting up for the proof, except for actually drawing CH. But we're going to join CG, CH, and CE. And this is what? Postulate 1, yeah. So CH is the line that we wanted, but we need to make CG and CE in order to prove that that's the line that we wanted. So we make CH, or CG, here's CE. That one might be a little bit off. And then CH. CH also seems a little off. Here we go. That seems good. All right. And then the claim then is that CH is perpendicular to AB. And really this proposition is requiring two different things, but one of them is kind of trivially obvious. One, we have to create the line that is perpendicular to AB, and two, that line has to pass through C. Well, yeah, obviously CH passes through C, so we're done there. So what do we need to prove? We just need to prove that CH is perpendicular to AB. And how do we do that? Well, first of all, we know that by construction, GH is equal to HE. So GH is equal to HE. That's from step 3. I'll say, I'll just say step 3. It's by construction. But yeah, by construction through step 3. Obviously, HC is equal to itself. That doesn't need any justification. We also know that CG is equal to CE. So CG is equal to CE. Well, and that comes from step 2, because they're radii of the same circle. So, what does that give us? Let's take a look at what we just said, what we just claimed. We claimed that GH is equal to HE, HC is equal to itself, and then CG is equal to CE. So, kind of we know today that that's side, side, side. So this is proposition 8, side, side, side. These two triangles are the exact same. Proposition 8, although was actually stated slightly differently. Proposition 8 was saying that if you have, I mean, it's essentially side, 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 but it's saying if you have two sides equal to two sides, and then the third side is like also equal to the third side, the angle between those initial two sides, the equal sides, will be the same angle. And then from there, that's you can use proposition 4 to say, well, okay, side angle side, then those two triangles are the same. So that's where the congruence comes from. But proposition 8 specifically says that So by proposition 8, we have that angle CHG is equal to angle EHC. So where are those? CHG is equal to angle EHC. And why is that important? Well, because since angle CHG and angle EHC are adjacent and equal by, let's see, definition 10. Definition 10 says if you have two angles that are adjacent and equal, then those are right angles. By definition 10, I'll just say they are right angles. Probably should be more explicit about which angles. Angles CHG and EHC are right angles. So we know that this is a right angle. We know that this is a right angle. So the result follows. CH is perpendicular to AB. And since this is a construction proof, that gets A, Q, E, F. There we go. Looks like the video is lagging a little bit behind what I'm saying. That's fine. All right, there it is, proposition 12.